recording. And we continue. So you can actually use this Nernst equation for example, determination of solubility products, equilibrium constants. And what I actually use this Nernst equation for is also whenever you measure pH, for example, you measure a potential difference between two parts of the pH electrode and then convert that to a pH value that is hidden in a way. But here is a lab experiment of determination of the solubility product of silver chloride. If we start with a cell that is only dependent on concentration of the silver ions, say that we have silver solidus and silver ions and silver ions and silver solidus and the same solution in both compartments. So in principle, we should measure no voltage difference, but in practice we measured 0.00176 volts, which is nearly zero, I would say. Probably we had a different type of silver pins here. They were maybe scratched in different ways or something like that, giving rise to small differences, or there may be some problems with the contacts or something like that. Essentially zero. We had the concentration of silver at 0.01 in both beakers. Then you can in principle calculate the reduction potential, since the reduction potential is the potential of this reaction. We only need to find the Q. Q is the right hand side divided by left hand side. All of the activities on right hand and left hand side. And here it's the activity of silver metal divided by the activity of silver ions, because silver metal is on the right hand and silver ions is on the left hand. Nernst equation. This is Nernst equation, and I would recommend actually always using this version, because it's never wrong. There are versions available that is perhaps not easy to apply to every possible cell. For example, the one that if you see a plus sign here, beware. But in this case, I took 1 upon Q instead of Q. And then I change sign of the minus here to a plus. So this should be no problem. So adding the E naught is 0.8 volts that you need to take from tabulated values. RT upon F, N is only 1. So I skipped the 1. Or Q is 1 upon the concentration, or the value of the concentration, which I stated here. If we want to skip the 1 upon AG and only use the concentration, then we invert the argument, and then we also get sign change in front here. But the idea is that the reduction potential, the E, is 0.68 volt instead of 0.80 volt, as it is on, this is E naught. Why do we want this? Well, afterwards, we added a lot of chloride ions in the form of sodium chloride solution, I think. Then silver chloride forms, and since silver chloride is a kind of insoluble compound, and we have a surplus of chloride ions, then I guess that the silver ions should be very small. According to literature, the solubility product of silver chloride is 2 times 10 to the minus 10, quite small, not very small, but quite small. So what happened in reality? After adding this sodium chloride solution to one of the beakers, we got a precipitate here, the white milky precipitate of silver chloride. And suddenly we measure a potential difference in the order of 0.46 volts. I would round this to 2 decimals. So what does it mean? It's a high concentration, this 0.01 still in the left beaker, and here is a low concentration. I have it connected to the negative pole here of the voltmeter. So let us see, can we use Nernst equation? I suppose we can. Now let's see where. So we know that the positive pole was 0.68, and we measure 0.46 volt as the cell voltage. That is the difference between the positive and negative pole. Since we measure the difference 0.46, and we know one of the endpoints, simultaneously we know that since we had minus to the beaker with the silver chloride, that must be below 0.68. So then we can construct the potential of the negative pole, 0.22 volts. Then we apply that to Nernst equation. 0.22 equals to the Nernst equation. The Nernst equation must be valid for, if it's valid for the left hand left beaker, it is valid also for the right beaker. So then we can calculate the silver ion concentration in the presence of chloride ions. And this is nearly everything that we need for the calculation of a solubility product, since the silver ions are determined from the electric measurements. The chloride ions, here I estimate, since I'm mixing 1 moles per cubic decimeter solution, and maybe the volume increased to a factor of 2 or something like that. So I estimate the chloride ions to be approximately 0.5. Then we can assume that the solubility product is approximately 0.8 times 10 to the minus 10. And comparing that to the literature value 2 times 10 to the minus 10. Well, it's not bad. It's maybe 100% wrong, but only 100%, not several magnitudes. Which one is wrong is probably me that is wrong, because I was using a sloppy setup for the electrochemical cell and such things. So if introducing yet another diagram, in the textbook you have, they are found of not only pore bed diagram, but even more of something called frost diagrams. Frost diagrams are convenient if you want to, now let's see. So if you want, we had the delta G equals minus NFE. So if you divide this delta G by minus F, then you would get something called NE. And this is what is given here in the frost diagrams. If you have delta G naught, E naught, E naught, and G naught. So the Y value here is essentially constructed from the E, yes, and the number of electrons of from the Nernst equation, but it's the essentially a measure of delta G. So simple, these frost diagrams, they are given as functions. The states are given in integer values as the oxidation number of the element. And the lowest lying point is the most stable oxidation state. So in the case of nitrogen here, for example, we see that nitrogen gas is obviously the most stable element, type of nitrogen compound in the whole nitrogen system, except ammonium ions, actually, at least in the acid environment. In acid, the red lines corresponds to pH 0 acid environment, and the blue lines to pH 14. And this is perhaps a disadvantage with frost diagrams. At least to me, I grew up with pore bed diagrams from the 80s approximately. I lived with them most part of my life. So I don't see the pH dependence very much in a frost diagram. It's usually just giving at the most common is at pH 0, and you can definitely use it for stating that N2 is definitely very, very stable. N2O is less stable, and NO, all of these are at a higher delta G upon minus F value. So they should be less stable. And also on the opposite side here. If you take a simpler frost diagram, this is for oxygen, oxygen gas. Is that stable? The delta G naught, upon F, delta G formation of oxygen gas is by definition 0. Since forming oxygen gas from elements in pure standard state is the pure standard state of oxygen is also oxygen. Here we see that hydrogen peroxide and water is at a lower value. So water is in this case the most stable oxygen compound. that one can see also from the reduction potentials. Now let's see, water. When oxygen is reduced first to hydrogen oxide, the reduction potential is 0.68 volts. This is a Latimer diagram. Latimer was some guy living in the 30s or something like that, and producing a book of all elements, Latimer diagrams, which is still used today. 0.68 is actually the slope here. I think if this is 0 and the distance here is 1, then the y values should be 0.68 or negative actually. The reduction potential, this is a positive reduction potential. So what does it mean? Going from oxygen to H2O2 means a negative delta G. Delta G is minus NFE. So this should be more stable, which fits with the Frost diagram. And then yet another 1.78 volt arrives at, this is the slope here. So this value here should be the distance between these two, should be 1.78. Since it's only one electron, oxygen goes from 0 to -1 and to -2. And the sum of it is 1.23. This is tricky. Let's investigate this. How come? I think we need to actually write some reduction formulas. If I can get the O2, gas goes to H2O2 AQ. This is balanced in terms of oxygen. So we just need 2 hydrogen. Now it's balanced in atoms, but not in electrons. So, sorry, too little space. 2 electrons. Now this is balanced, and this is the E naught is 0.68 volts. Means that the delta G of this reaction is minus, it's 2 electrons, 2F times 0.68. Okay, let's go for the second one. H2O2 AQ to H2O liquidus. What is it? 2 oxygen here, it's only 1, so we need 2 of them to balance oxygen. Here, now we balance hydrogen, so we need 4 hydrogen. We already have 2 of them, so we need 2 extra hydrogen ions. Now everything is balanced except the charge. So we need 2 electrons. Now this is balanced, and this is the reduction potential of this is what we should arrive at. This has the reduction potential as 1.78. So let us check the delta G is minus 2 times F times 1.78. I would like to mention that energies can always be added, but potentials are dependent since they are dependent on number of electrons. They are not directly. The sum of these two is not 1.23. But suppose if we go this way from O2 to Hopsan, sorry. We should go from O2 to H2O directly. Here we, in order to balance this, is 2 oxygen, only 1 here, so we use 2 water. Now it's balanced in oxygen, but we still have the hydrogen, so we need 4 H plus. Now it's balanced in all atoms, but not the electrons. So we need to add 4 electrons. This is the reduction potential 1.23. But now let's see. I'm a little bit out of space. Maybe up here, yes. If we take oxygen to H2O2, and then forming this H2O, letting this H2O2 to form water. Now let's see, 1 oxygen, this is 1 oxygen gas forming H2O2, and this is only 1 H2O2 reacting here, forming 2 waters, and we have 2 waters here, 2 hydrogen here, 2 hydrogen here. This makes up to 4 hydrogen, 2 electrons, and 2 electron make it up to 4 electrons. So it seems that this delta G is the sum of the red delta G, red, plus the blue delta G, which is equal to minus 2F times 0.68 volts here. And then the blue delta G was minus 2 times minus 2F times 1.78, which is equal to minus 2F 0.68 plus 1.78. What is this? 78. 8 and 8 is 6. 5. It's 2.46, I think. And then if delta G is now it was 4 electrons here. So if we say it's 4F times 1.23, it will be equivalent. This is half of the computed addition here. This was really messy figure, but 1.23 is the sum of 0.68. This is one electron, and this one is also an electron. But no, it was 2 electrons because it was 2 oxygen atom, and here is also 2 oxygen atom. But here is 4 electrons. So if you interpret the potential as the energy per electron, this fits actually. This is 2.46 volts per 2 electrons, or not per 2, for 2 electrons. But for if we split it up on 4 electrons, this is for 4 electrons. This you need to sit down with paper and pencil, I think, in order to convince yourself. There are several of these Latimer diagrams, and there is also, if you Google on the internet for Latimer and Frost diagrams, you will find very nice exposes for how to use them and interpret them. One can say here is some collection of different stuff for the Frost diagrams. If you have 2 elements, 2 forms of an element that are joined by a third one, and if this third one is above the common connection line here, then one can say that this item has a possibility to form the other 2, and that would in principle mean that on average it would lower its energy. One says that this is a disproportionation. This is not so uncommon. Typical disproportionation could be, for example, chlorine gas that forms a chloride ion and a hypochlorite ion, for example. Sorry, here we need water also. And then we get 2 hydrogens. But it's a splitting of oxidation states from 0 to -1 and +1. There may be reasons to against this, kinetic reasons that a compound may be stable, but at least from thermodynamics, it may go down to a lower level, formally lower level, but in practice it will form these 2 mixtures instead of the element in between. And the opposite, if you have 2 elements that are at a very low level, and you have a neighbor in between here with a lower than average value, then it may be so that this one and the lower one here forms the lower lying neighbor here. This is the opposite of disproportionation. They call it comproportionation. I can't pronounce that. We can look at the manganese, for example. Different information available in frost diagrams and pore bed diagrams. In a frost diagram, you can directly see that in water solution, the manganese 2 plus is the most stable because it's the lowest lying. Manganese has 0. Manganese is not visible here in the pore bed diagram because it's far down. Actually, manganese is quite non-noble and quite reactive. It's not common to have pure manganese metal, but manganese 2 plus seems to be stable. This is the same arguments that one can see. Manganese 3 plus, where is that in the pore bed diagram? I don't know. But manganese oxide, that is present in the both in the pore bed diagram and in the frost diagram. Then we can perhaps explain that this manganese 3 plus, if we draw a line here in between these two, we see that manganese 3 plus aqueous is above the connection line, so that will some of them will oxidize and some of them will be reduced. So manganese 2 plus is not present here in the pore bed diagram because the pore bed diagram only illustrates stable species in the aqueous environment, while the frost diagram illustrates even more species, also those that are not stable but that decompose. And that is, of course, a nice thing. This is pore bed diagram at pH 0, so it's essentially only the information at 1 pH value. If you want the pH character of the chemistry, then you need to have this pore bed diagram. If you want the more details about other species, then you need to have the frost diagram. One can say that the frost is a projection in a third dimension, maybe, of the pore bed diagram. So now let's see. Time is 45. I think we should manage with the rest also. So the last type of diagrams that we are going to introduce is called Ellingham diagram, after some guy, Ellingham, I suppose, or woman, I don't know who he or she was. If you plot the Gibbs energy as a function of temperature, delta G is delta H minus T delta S. Then you should get some kind of diagram. And the red line here indicates the formation of metal oxide from a metal. Suppose that we should have some kind of metal. We take this copper oxide. We take copper solidus plus half oxygen gas to copper oxide solidus. So delta H is probably negative. Probably. Otherwise, it's not a stable oxide. And do copper form an oxide? Is copper oxide a stable oxide? Yes, it is. Delta S then. this is a solid and this is a solid with very low entropy. But this is a gas, and gases in general have much higher entropies than solids. So delta S is low minus low, that is more or less zero, minus a large value here. So delta S is probably, now let's see, 0 minus a large, it's less than 0. This is strange. I mean, why is copper forming an oxide together with a gas? How come that gas can be consumed? Well, it's only because the delta H is very negative. Negative, if this is a negative value, temperature is always positive, at least bigger than 0. Negative times negative makes uh, the total delta G a line that increases. So at high temperature, we may reach some value where um, delta G of the formation is bigger than 0. And then perhaps from a thermodynamic point of view, the oxide shouldn't be stable. Um, here we have the copper oxide actually plotted. Hoppsan. Sorry. Here is the copper oxide plotted, the formation of copper oxide. I don't know, this bend here is probably because some of the either copper metal or copper oxide melts or vaporizes or something like that. You see here that at low temperature, copper oxide is stable. It's negative formation of delta G formation. But the higher the temperature, at some temperature it goes above 0. So just for the case of copper oxide, this don't heat this one too much, then it will disintegrate. There could of course be a lot of other things that happens, but this is just showing, this red line here is just showing this very reaction, assuming also that delta H and delta S is independent of temperature, which is far from true, but at least it is an approximation. This diagram shows a lot of different metals. For example, aluminum, the formation of aluminum oxide. It's that line. One can ask, formation of copper oxide or formation of aluminum oxide, which one? This is probably per oxygen atom, because it's 1/3 aluminum oxide here, and here's a full copper oxide. Which of these two oxides are the most stable? Well, it's definitely aluminum oxide. So if you would have copper oxide mixing it with aluminum, then you would get copper metal and aluminum oxide. Now let's see. Sorry. Plus AL 1/3. Then we need 2/3 of aluminum. Strange balancing, but this is actually correct. So then at this temperature, you can sort of disintegrate the copper oxide, while then forming aluminum oxide is much more energetically favorable. When it comes to formation of carbon dioxide from carbon, this is a special type, carbon plus half oxygen to no, it's a full oxygen. Äsch då. We can take it like that. CO2. So delta H is definitely negative, but delta S, this is a gas minus a gas, and then it's a solid compound with very low entropy. So this is one of the few lines showing a formation of an oxide with essentially no slope. And even more strange is the formation of carbon monoxide from solid carbon, because that is carbon plus half oxygen down to carbon monoxide. This is gas and this is gas. This is a full mole of gas, and this is only a half mole. So one large number for the entropy term minus a half a large number. That will be a positive. And since delta G was delta H, which is clearly negative, yes, minus T delta S. If this is positive, then we will have a negative slope of this. This is one of the few oxides that are actually having more and more negative delta G formation as temperature increases. So also carbon monoxide is quite poisonous, so avoid heating carbon and burning carbon at very, very high temperature, because then the formation of carbon monoxide is thermodynamically more favorable than formation of carbon dioxide. Of course, you can compensate that by adding a lot of oxygen to shift the equilibrium towards carbon dioxide. But still, say if you go to 2000 Kelvin or so, it is a risk of forming too high to be healthy, at least, concentration of carbon monoxide. Could be of interest when you are using your graphite surface furnace or something like that. I don't know if you have one of those still. This is the last figure. How many minutes? We have 5 minutes to 12 o'clock. Yeah. It is of interest actually to use these diagrams. For example, in iron production, here we put in an iron oxide and some carbon or carbon monoxide. That is also a possible reduction state, and forming magnetite together with more carbon monoxide form wustite, and it's a lot of carbon monoxide here because it's gaseous, and in that respect it's has a lot of access to the iron ore. And here iron is produced and then melts, and then you can get rid of surplus carbon in the iron, and then just tap it off here, and then one can build and use this iron as construction material. This is very important industrial process. Some metals, they are formed as sulfides, and you can draw these pore bed diagram. No, these Ellingham diagrams also for sulfides and in general any compound. But you can't reduce zinc sulfide with carbon. You can reduce zinc oxide with carbon. That's no problem. Plus carbon monoxide. But if you look at the formation of carbon sulfide, it's this line. And it's not very negative, it's hardly stable. At least compared to zinc sulfide. And most other sulfides also. Iron sulfide. Iron sulfide is an important iron ore. So in order to use the iron sulfide or zinc sulfide for reducing with carbon, this is not possible because the carbon sulfide is less stable. What you do is that you take this sulfide and expose it to air. Then you will have, among other things, SO2, because the sulfur, the oxygen's sulfide, or we usually know it as sulfur dioxide, is very stable. This is called roasting. We roast the sulfide ore. So in principle, you would get zinc maybe, but heating it up with the oxygen accessible, that would produce zinc oxide. But on the other hand, after roasting the zinc sulfide ore to get zinc oxide, then you can mix it with carbon and get zinc metal. This is actually what I had to say, and clock is 11:59. I've never been that exact in time before. Should we have a lunch break? Are you still there?
Yes.
Yes.
Yeah. maybe you've fallen asleep from my voice.
No, of
Oh,
course
no, not at
not.
all.
I apologize for, but we can see each other 1 o'clock. I mean, there are some exercises we can, if you like, and we can have some discussions. I can show you Medusa, how to use Medusa for this production of the pore bed diagram. That is quite fun, actually. It's very convenient to have a tool that enables one to draw diagrams and draw conclusions about chemical reactions. So first, some lunch. See you 1 o'clock. Is that okay?
Yes.
Yes.
Yeah.
See you.
Fine.
See you. Bye-bye.
See you. Bye-bye.